thanks very much for coming after the summer. Welcome back to Cambridge AI. We've got a really good event tonight around AI in Agritech with some fantastic case studies. Before we get started, I'm just going to hand over to our very kind sponsor, RedTech, and this is Robert Bull, who will tell you a little bit about RedTech.
So we are and first of all, good evening everyone. So we are a specialist technical recruitment agency based in Cambridge. I could probably stand here for a very long time and tell you everything about us, but what I'll say is that we set up about 6 years ago now. We are recently expanded into the USA, so we do not just a lot of technical recruitment in and around Cambridge, but also, like I said, US, graduate hiring as well. And some of the stuff I think that, you know, as an owner of a business, what I'm most proud of is we are one of the highest rated agencies in the UK. We have a pure 5-star Google review, so over 100, I think 101 now, reviews. We also have a great following on the socials. So I think we're now on LinkedIn, 50,000 followers on LinkedIn. And really exciting is, I think last month we had our first ever viral Instagram post. We had over 100,000 views for a cat missing its co-worker. So yeah, so basically long short of it, if anyone wants to chat to myself or my co-founder Rebecca, I've also got Mo here tonight as well, who does our business development. Please come and grab us if you want to generally talk to us about hiring in Cambridge, or if you're a candidate looking for work, we're more than happy to have a chat with you. And any questions about recruitment in general, we're more than happy to support you. So thank you everyone, and over to you, Mark.
This event is also brought to you by Grounded AI. We set this event up a couple of years ago. In fact, the first one was here. And the idea of it was that we thought it would be helpful if there was an event in Cambridge around AI that was focused more on case studies and less on, if you like, the kind of slightly highfalutin end of talking about the possibilities of AI, but more about the nuts and bolts, really focused on the needs of the Cambridge population, which is obviously much more around engineering and so on. Grounded AI is a business that is focused on verification. We have a product called Veracity, which is being used by academic publishers to essentially check the validity of citations in academic papers. If that's something you're interested in, you can find it on that URL. We work with a number of big publishers, really combating the rise of unsafe publications in academic publishing. So that's Grounded. For the event tonight, I'd like to introduce our first speaker. Our first speaker is Garner. He's from Antler Bio. Ian is an R&D leader with a PhD in epigenetics and a multi-omic oncology bioinformatics background. So that's a mouthful. As head of R&D at Antler Bio, he's built scalable, cloud-based RNA-seq pipelines and AI-integrated tools that convert raw transcriptomic data into real-time actionable insights, advancing precision agriculture across the dairy industry. Now, that was quite a mouthful. I'm sure he'll make it make much more sense in his presentation, which is all about how you get more milk out of cows. So Ian, here he is. So Ian Garner, everybody.
Thank you for inviting me to talk about Alex and RedTech recruitment as well. Thank you for this opportunity. Yeah, sorry, it's a bit of a mouthful. Basically, I have a PhD in epigenetics from University College London, and I did a lot of cancer informatics research at Imperial, and now I'm in Agritech. COVID hit, and this is the route I took. It was very exciting though, so I'll just jump straight into it at what Antler Bio does and who we are. We were founded pretty much during COVID, 2020. We were basically three full-time employees for basically until last year, and now we've grown to 28 employees, 12 full-time, 16 part-time. And during that time, basically what I want to kind of get across is how AI has actually helped us scale, and show how it's helped communicate with a lot of different stakeholders. We are all our dairy cows that we look at are in Finland, Sweden, and now they've just started to get into UK. But before it was just Finland. So we use something called gene expression data. So you'd have heard of genetics, maybe. You might have heard of epigenetics. They both can regulate gene expression, but no one's looking at this in dairy science. So why do genetically similar animals have different performance? Oh, sorry, I realized I should be holding this up. So you can get very genetically similar animals, but if they don't express the genes at the optimal time, then they'll get a suboptimal outcome. The reality doesn't reflect the potential. No one's looking at that expression data, and that's the key data. You can have great genetics, you can have great versions of genes, but if you don't express them, it's kind of irrelevant. It's similar if you had like a great car, you could have a Lamborghini, or you could have a Nissan Micra. You'd probably choose the Lamborghini, but if it doesn't have fuel, if it doesn't have the right electronics, then it's not a car, it's just a lump of metal. You'd rather have a Nissan Micra. So very quick overview, how we do this. We do a blood test, we extract RNA, we collect metadata, phenotypic data from the cows such as milk yield, milk fat, milk protein, cell counts. There's 153 different metrics that we collect. And then we basically take a proportion of a herd. We take about 10% of a herd. We take good cows, we take poor cows. We statistically select the ones we want. And then we look at what are the differences in gene expression. So there's about 27,000 genes in a dairy cow. We look at all of them. We combine all that data together and do bioinformatics on that. We have done machine learning on that, although we're building to that point where it makes more sense to do machine learning. And then we use AI, our own integrated tools, to add context to the genes, add context to the pathways, our recommendations that we give. And then we basically say to the farmer, here's what the data shows. If you want to do anything with that, great. If you do, let us know. We'll capture that impact. And then over time, we'll see how that affects milk yield or other economically important traits. So the challenges so far and where AI has really helped us, we were and are still a very small team, relatively. We had to prove this, that we can scale, we had to be efficient, and we wore many hats, as all startups can probably appreciate. There are adoption barriers. Many farmers are often wary by genetics. They have been told genetics is the solution and it doesn't live up to the reality. So it's already difficult to then say, well, actually, there's a new technology we can help you with that's very linked to that. And to show impact, we need to get data. To get the data, we need adoption, and to get the adoption, we need the impact. It's a catch-22, it's a vicious loop. AI has enabled us essentially in 3 areas. There's 2 that I'll briefly touch on that are quite obvious where AI could have helped us, and then there's one that probably resonates far more with what Mark's doing in grounded AI, where we've developed a tool that harnesses that knowledge, that scientific literature, to support our recommendations. So when vets or nutritionists or animal experts say one thing and others might say another thing, we can add that context through AI and give scientific clout to what they're saying. So firstly, again, I'm a bioinformatician with wet lab experience. I'm not a cloud engineer, I'm not a solutions architect. We didn't have money to employ people like this when we first started. So I know how to develop pipelines for audiomics purposes. Built this in the cloud. AI just really helped us accelerate that. It optimized code, it catched inefficiencies, it speeds up integration of third-party tools so we could show a variety of stakeholders where we are and what we're doing. We can rapidly change pipelines or improve them with the help of AI as well. And this obviously reduces manual overhead. You don't need teams of bioinformaticians to build this if you just keep using AI as an enabler. So this is a little bit of a messy slide, but essentially just shows data flow, Lambda functions. I had very little experience of writing Lambda functions in Python, but with AI I was able to then build other things into that. So this really enabled us right at the beginning to scale, build a very efficient and scalable pipeline. The potential use of AI here in the future would be if we perhaps, and this is not something we're doing at the moment, but it's something that might be relevant in the future. You can get agents that can automatically detect if there's something wrong in your pipeline. You can, it will then know perhaps where to find the files to look for. Maybe a different type of analysis is needed. You can containerize that. It might be a useful feature in the future. But again, very brief speed run almost of how that helped build this pipeline. The second one is pretty obvious, but maybe not obvious to everyone. We're working with Finnish farms to start with. I don't speak a word of Finnish. Yet I have a 58 email thread, long email thread with a Finnish label supplier where I haven't spoken a word of English. AI allowed me to do this. We can directly talk to farmers in Finland. Not knowing Finnish is a very difficult language, I'm told. I wouldn't know, I've used AI to help me with that. But it's allowed us to convey very complex biological concepts to a variety of stakeholders in another country, whereas before that would have been impossible, unless you've got Finnish-speaking team members that have time to do that, which the CEO is Finnish. We had a part-time salesman who's Finnish, but he's busy trying to sell the product. So this really helped overcome that, not just a technical language barrier, but also an actual language barrier. Where I'd like to spend a little bit more time on, where we've actually used AI in maybe a more unique way, which touches on what Mark and Grounded AI are doing, I believe. Like I said, when vets give a recommendation, why would you believe that vet over another vet? They might both have the same recommendation, but where's the data behind that recommendation? Is it current? Is it still valid? We're working with some dairy farms who are very high end. If you think of like athletes, they're going to have different requirements than the standard person. So the recommendation should be different, logically. There's very limited data out there on bovine gene expression. There's no publicly available RNA-seq data. When AI models became public, I think at the end of 2022, roughly, they did a lot of hallucination, if you like that word. You would make up references, right? And that's kind of, I think, Mark, where you're coming from with Grounded, you want to solve that. We also wanted to solve that. So we built a model or a program where we could basically look at all literature in existence for given search terms, and then extract gene data from that. So we have a list of all our genes. We have a list of search terms that we want to look at, say milk yield in dairy cows, or what are the effects of omega-3, omega-6, etc. So we built our own knowledge base with this program through basically just logical code. No AI here at the moment, but where AI really excelled on this was it provides context to what we were saying, and also we could apply a RAG-based approach where it only looks at our knowledge base, only our data set, not all data in existence. So an example here is, if you think in human science, breast cancer, ovarian cancer, you might have heard of BRCA1 and BRCA2, they overlap. Anyone in that field will know that, but they won't know all the other genes that overlap, perhaps. In bovine, in dairy science, you wouldn't know probably anything that overlaps. So this program allows us to do that. It's probably a little bit small, but the plot down, is there a laser pointer? If I just put it. This plot here basically just shows the top 30 genes that overlap in literature for omega-3 and omega-6 in dairy cows. So these genes are affected by omega-3 and omega-6. You've got a list of, again, the top 30 based on publications. So we know there's 10 publications that mentions TNF, a gene, tumor necrosis factor. So all these different genes we can identify, we build that knowledge base, we segment, we collect all the metadata associated with that, such as the abstract, where it's published, how many citations, everything you can think of basically to do with the paper. And then we break that down, we use a RAG-based approach, like I said, and then if we have a question, how does omega-3 affect milk yield, then we will get a far more accurate answer with very minimal hallucination, with actual PubMed citations where you can go back to, so you have a source of truth. So if you think, if a vet says you don't need omega-3 in your herd, or you've got plenty, we can say, right, with our gene expression data, we see that these genes have been talked about in the literature that are associated with omega-3. We can see they're different between your top and bottom performers. Here's all the literature summarized in a little paragraph with citations that you can believe. and then it gives that extra credence to what the vet's saying, or it helps change that mindset maybe. A classic example is we had one farm where the nutritional expert said you're getting enough vitamin D from just looking at the feed and stuff. You know, you can't tell that from just the feed. The animals, when you looked at their gene expression, they had differences in vitamin D genes that metabolize vitamin D, which essentially means that they're not converting it, or not able to express those genes. They're not going to be able to convert vitamin D into their active form. So a recommendation there would be to give the active form over just vitamin D. And then we can use this to provide all that information grounded in truth, and then go back to the farm and say, well, actually, look, here's what we see. This is a layer of data that your nutritionist didn't have before. Here's all the references that are linked to that search term. You know, who do you believe now, kind of thing. And this is a kind of again, a report that we can generate. This takes about 30 seconds in dairy science. It takes about 4 minutes in human. It's not optimized. It's kind of just showing how we've used AI to get to where we are. It provides a bit more context, so we can see where publications are published. We can put a contextual analysis down here, which just gives a very basic AI overview. Sorry. I didn't know I'd put on so much weight over the holidays. Yeah, it gives a little contextual analysis, and then any question you ask, it will give you grounded truth, essentially. I'm sorry for using that word, not. I know your company's called Grounded. But yeah, that's allowed us to break down this barrier of trust, essentially, and give actual scientific evidence support. We don't have huge amounts of money to do lots of clinical trial studies on different farms. That's just not feasible. So when we need to say or offer support to what we're saying is true, then we can look at the literature and see what has worked, and we'll provide that to our farmers. And then as we capture the impacts they make, they're more likely to make those changes. Then we can start seeing, right, yeah, this did work, or actually this isn't as efficient as we thought, or maybe not. Maybe it works, it's not cost efficient. Maybe it's really cost efficient. So yeah, that's basically just a summary, really quick summary. It helped us initially speed up pipeline development. It optimized some of our code. We're not using it to replace anything, we're using it to enable us. So we always, everything we do, we have vets that will look at it, nutritionists, so we don't rely on AI. We use it to speed up development, and then we validate it with our own vets or nutritional experts, etc. It helped us communicate to early adopters really well. And then it's also helped to provide this scientific support to what we're saying. We are looking at now using agents. We're not too far on that at the moment, but it'd be great to have some side bots or agent style AI on our actual app. So our actual app is called EpiHerd, where farmers can log in, review their results, look at their recommendations. It would be great for them, rather than email us any questions, to actually have a side bot or an agent that can do analysis on their own data, so that they'll get a lot more out of that, and we won't have to spend a lot of time of our time. It will enable us to do more. It also is going to be really good at turning unstructured data into structured data. So farmers are always busy. They don't want to sit at their computers and send us details. If they can just say, send a picture of a barn, the lighting, we can use AI to turn that into structured data and say, yep, this barn's got really good lighting. Great, because lighting affects gene expression. Or maybe it looks and sees no windows, so actually the ventilation's no good. Ventilation affects gene expression. So we can pull that data and build that knowledge through AI by turning unstructured data into structured data. And we're also looking at, we've got a few proof of concepts out at the moment, looking to identify business opportunities and also do some more pipeline development. So that's where we're at the moment. I think without AI we wouldn't be where we are. It has enabled us. Yeah, thank you.
So I had a first question, which was, if I'm a farmer and I'm using you, how do I know that you're working? What makes me want to recommend your service to my farmer neighbour?
question. You might not want to recommend us to your neighbour if it's working really well. If your yield's going up, we basically say, here's recommendations that will help your yield go up. Here's the proof. This is what the gene expressions data say. This is what's known in the literature. That's where we kind of leave it. If we don't push anything on the farmers, that's how we build the trust as well. We don't say, right, you need to use this supplement, or you need to go to this company and get this product, or whatever. We just say, here's the data, go and consult with your nutritional experts. Here's the proof, here's the citation, here's all the data. And farms do make the changes, we capture that data then. So we say, right, let us know what you've done. Okay, you've added vitamin D. How much? What company? What brand? Are you still using it 6 months later, kind of thing? We have real-time access to their data. So every day we can see if their milk yield goes up or not. So we run models then, just before or after at the moment. But we have some machine learning models in development. But yeah, we see like a significant increase in milk yield because when they add vitamin D, and as more and more farms do the same, we can then say, right, okay, 50 farms have made a change in vitamin D, their yields go up 15%, this is clearly working. So then we now know that this is, as long as it's cost effective, because we'll capture that information as well, then we can say, right, this one is working, this literature is correct. And that's how we build our confidence of what one was. We have others where they're not as good. So we drop those recommendations, we bring in new ones, or we modify them. If that makes sense.
Thank you. Any questions from folks here?
The source for the literature you're processing, like, is it only archive and maybe some publicly available publications, or do you have access to some private ones? Are the public ones enough, is the question, and what do you do about that?
Yeah. So we only look at abstracts from PubMed, so there's about 45 million, right? On PubMed. We can hook up to lots of databases if you want, but this serves what we need at the moment. The good thing about abstracts is you can identify gene names uniquely. Usually they will say, this is what we've looked at, rather than go through the entire paper, which then gives lots of gene names where they reference others. So with the abstracts, we're able to see very quickly, like, these genes have been mentioned in this context. We pull all that data and we say, right, this gene's mentioned once on this abstract. If it's mentioned 10 times, it's still only once for that abstract. We reduce it down. So everything's publicly available on that. We just access the API on public.
So abstracts are enough for
what we need to do to be able to add proof.
Harris?
I'm interested to know more about how easy it is to sell to farmers, and do you find it easy to sell to farmers? It's quite known that in the UK, very tight margins, and I don't know how they survive. So how would you price that? Is it? Maybe you can comment.
Yeah, it's a great question, and it's exactly what you said. It's very difficult. Like, farmers don't have much money; they're not capital rich. We've started with early adopters. We're lucky we have early adopters in Finland to be able to say, does this work or not? And it's been an overwhelming success in Finland. It's now spread to Sweden, and now it's starting to come into the UK. We're very lucky as well with our investors who understand Agritech and deep tech. That kind of crossroads is quite unique. And also Innovate UK have been brilliant. We've had free grants in the first 2 years of the company. So that's really helped. So we've been able to subsidize a lot of it. The margin, like, is an expensive technology. RNA-seq is expensive to us. We don't make much money, but we're hoping that once we show that it does work, that it can improve, that then we can offer guarantees perhaps. We've started offering a little bit of a guarantee because we are seeing so much success. So then we probably should raise prices, because farmers are making, some of our farmers are making 20% increases in milk yield. That's tens of thousands, if not hundreds of thousands a year. And we're charging 4,000 a year. We should probably look at that.
John?
The reports that you generated, they look fantastic. They reference in all the scientific literature. How do the farmers respond to that? Because they're not traditionally known for their scientific insight. So how do you do the translation from scientific technology into?
It's a great question as well. On our recommendations, we break down that science. So we include the references. They can click a button and then it shows the references that they want to see it. Otherwise, it's plain markdown text essentially with very broken down biology. And this is what we see in your data. It's easy to read. It's not scientific for them, but they can have it scientifically. If they go to their nutritionists or their advisors on farm vets, then maybe they have a bit more knowledge, and they can read it and say, okay, this makes sense, or okay, this doesn't make sense. Like, it depends. We had one example where a farmer really wanted to, like, they bought the package, they got their results, they got their recommendations, and they chose to ignore them and go with advice on their feed expert that they just employed, and their milk yield tanked, and they fired them, and they went back to us and went back to recommendations. They resequenced, we got it back to where they were, and now they're doing far better. I'm not saying that that's the same for everyone, but I always say the science, like the data doesn't lie. You can interpret data incorrectly, but if you put good things in, you'll get good data out. You just have to work with that. We don't push anything. We just say, here's what it shows. This is how we've interpreted it. Here's all the other proof. Here's, we're starting to show now recommendations that are really having a significant effect across multiple farms. That adds a bit more trust as well. If farmer ABC have done it, then why shouldn't I?
Brilliant. Thank you very much. So it's sort of money ball for cows. Fantastic. Thanks very much, Ian.
Thank you.
So our next speaker is Glen Slade. Glen started at INSEAD with an MBA and has 30 years of international management experience spanning IT in several life sciences sectors, and is passionate about changing the world through technology. Glen.
Well, good evening, everyone. Thank you very much, Mark and Alex, for the invite. It's great to be back at Cambridge. Before INSEAD, I did my degree in computer science here at Cambridge. I can't believe that was 40 years ago, what was then a 2-year computer science tripos. And at the end of that, I took the difficult decision not to do a PhD in artificial intelligence, but actually to go and get a job. My first job was as an IT consultant, and the relevance is that at that time, what was the bleeding edge of IT, I guess, or at least the commercial edge of IT, was office automation. So it was the time when our ancestors used to use paper in the office to get things done. We had to get those first PCs in there. And the relevance of this is that the golden lesson I took away from that phase of my career is that when you take a human process and convert it to a computer process, never do it the way the humans do it. And an easy example is if you, in the old days, used to have things called sales order forms, which would be in triplicate, and one would go to production, one would go to finance, one would go to sales. But obviously, as a computer system, you want one piece of data in one place, and you have to rearrange the architecture, rearrange the way you look at your business process to come up with a better solution. And that's really how come I ended up trying to rethink and reimagine the way people rear insects and process them with robotics and AI. And so I need to just take a detour and explain why on earth people might want to rear and process insects. There's something called the sterile insect technique, and it's an alternative to chemical insecticides. I discovered this about 13 years or so ago, and have since become sort of a believer in, you would obviously want the world to use sterile insect technique instead of chemical insecticides when you can. Not only is it more environmentally friendly, it also works better than chemical insecticides. And the only reason we don't always use this everywhere is that it's very expensive to make lots of insects, and then even harder to sex sort them in their millions. Typically the female is going to damage your fruit and laying their eggs, or distract the males that are meant to mate with the wild females. So you do need to do that sex sort step. And there's been a number of startups who've tried to solve these problems so that we can have SIT on our crops. I worked for one of them for a while, which did GM, but what I saw was, apart from the GM regulation, the key issues they had were scaling production, because insects don't scale easily. Each batch is an ecosystem, and if you make them bigger, you just get a bigger mess. You don't get more widgets. And so what we did was came up with a way to do this with robots. The other thing that you get as you scale up is you get more contamination. And so I ended up with the idea that if we make the batch smaller, ultimately a single insect, that's the way a computer and a robot would approach insect rearing. So I'm just going to get my little prop here. So this is the pot and lid that we currently rear insects in individually, and our current pest insect target is called a spotted winged Drosophila, Drosophila suzuki, for any biologists in the audience. And I'll show you a quick video of how our system works. I don't know if the sound's going to work. If not, I'll dive in and do the sound, but let's see. Sound. Okay, so here we go. Here's our green pots, and having oriented them properly, we need to fill them with 50 microliters of diet. So we've got a simple dispenser machine that's squirting that in there 3 times a second typically. The pot then goes into a special cage where the insects can lay an egg into the diet, and then comes our first use of AI. So what we want to know is there an egg in this pot? If not, it goes back in the cage, try and get an egg. If there is an egg, then it gets popped out of the system and goes down the belt to collect one of these lids. If you remember your biology, egg hatches, insect life cycle, becomes a larva, caterpillar, then it becomes a pupa, which is the cocoon, and then at some point it will emerge into adult. Biological variation says it could be anywhere between day 12 and day 16, so we look once a day. If there's no adult visible yet, it goes back into the system. Again, that's with AI, looking for the adult. If there is an adult visible, it goes through, we knock them out, but we just cool them down so they go to sleep. Then we spot the males and females with AI. Males go into release vials, wash these, we're very sustainable minded, and then we go and irradiate the males before they go to the field, which sterilises them about 90% or so. And there's one of our workers releasing them on a leaf. That's just the Photoshop. Usually just walk down and shove them out and they fly and disperse. So, being an AI talk, I thought I'd say a little bit about the first of all, the 3 main enabling AI functions. So these were the 3 things I sort of foresaw when I sort of came up with this concept of let's do sterile males individually. The first one is this egg no egg step. This photo shows actually we've got 2 eggs in the pot, and over the years we've got reasonably good at this now. We get about a 3% false positive, which is at the level which it doesn't really matter to me. It just means there's a few spare pots and we just have to, there's a bit of overhead. It'd be great to get it down to 2 or 1, but it doesn't really matter. But it's taken a long time, and you can't see it in this picture because this one's a recent picture. But the real issue we had is that when you shoot that 50 microliters of diet in the pot, you get all these micro bubbles. I mean, this is 5-6 millimeters across the red bit, right? So this is all quite small. And those micro bubbles, when you're trying to light it and get a good AI pick, looks like a white egg. So that caused a lot of problems. We've tended to use things like polarizing filters, careful choice of the angle of the light, getting the right color contrasts, avoiding white materials, which can also have flecks of cotton looking like eggs. Getting the focus right is quite difficult. Autofocus isn't a solution because it takes too long to find the focus, so we need to get the right camera, the right depth of field, the right positioning. So it's the usual thing. So it's very easy in principle. If you told a student you've got half an hour to train an AI to do some eggs, it'd probably get a good go at it. But getting it sort of refined so that it's an operational process. We now do this operation over 1 million times a day, and we learned along the way. Next one, very quickly, adult, no adult. So we're looking through the transparent lid to see if we can see an insect. There's a couple on the, there's 2 pictures there, both of which have got an adult. The key issue we got there is when flies get hidden, they can be either down in the diet or just slightly out of view of the camera, or up on the lid where you've got that little blister that sort of can also confuse the image. And as we're getting more cycles of washing the chimney, if we get something with a bit of dirt on there, that can also mess things up a bit. And then the last one, male, female. The difference between a male and a female spotted winged Drosophila, you can probably just about see. The males have got these 2 little spots on their wings, and that's a female for comparison. Now, that's an obvious one. That's the way someone like me can tell the difference between them with the help of, usually with a lens, because my eyesight's not that good on these little bits. But the spots only appear on the male after about 4 hours, and we're potentially processing them after they've just emerged. So the AI has to be able to do better than that. You can probably perceive that the female, bottom left, is slightly rounder and fatter, and the male's a bit thinner. And then if you get into the real detail, there's also things like things called sex combs on the male's forearms, sort of like these little bristly hair things. So there's a lot of other things in there, but the AI is just using, the typical AI thing, just using all the factors available in the image to get that right. And we actually these days have a third classification, which is dead. You can actually tell a dead fly from a live one, and that saves us sending dead ones to the field. So those are the three first ones. Back in 2022 we could do that. That was part of our initial end-to-end demonstration of the system. And of course the algorithm has got better over time, but really what we've spent the last few years getting right has actually been much more focused initially on getting the mechanical reliability of the system. Our 2023 system, which was built for high volume, was basically breaking down faster than we could fix it, which wasn't very good for production. So we focused on that. We got it mechanically reliable. We then got too much fly death, so we had to focus on the biology. And now with the biology fixed, we're now in a great new place. And I've really enjoyed the last 6 to 9 months, because as we've built the system and seen at last it works, what we now want to do is make it more efficient. Not get rid of our operators. I love my operators, but what we want them to do is to get our operators to be able to cope with more and more production volume, because as it is, it's a huge cost. We run our production line 24/7. Currently have 5 people on the line, but what that means to have shift cover is actually I've got to employ 4 people for every person on the line. So I'm hiring 20 people to be able to run this factory. Not profitable, but now we need those people because these little pots tend to get stuck. That was one of our sort of realizations with the mechanics. It's 10 millimeters across, but if it's going down a channel, there needs to be 10.5 millimeter wide channel. If it's too narrow, it gets stuck. If it's too wide, it sort of does a zigzag and gets stuck a different way. So we end up with a sort of semi-precision engineering and quite a tendency for things to go slightly wrong. So our operators have to keep an eye on it and sort of give things a prod if they're getting stuck. But of course, AI can help us with that. And take the middle picture first. This is one of the great sort of first steps which sort of helped us realise that AI can be the main driver to self-efficiency for us. As these pots come into today's gate, the one in the video is a couple of years old, they're coming down a metal channel. And the one on the left is how it should be. The pot in the middle is in a queue, there's one above it and there's one below it. The pot on the right has got stuck. There is nothing below it, and it's not centered on that. Now this, if anyone is into programming AI, is just using OpenCV, it's not using actual AI. And of course, we have to use the right tool for the job and not just use AI because we can. But we've also done things like use AI to detect bad pots. By bad pot, what I mean is the diet's getting old and dry, and then it shrivels up. Flies don't want to lay in it. If they lay in it, the larva might not survive. And that's a much harder one to sort of spot if the diet level shrunk down. But we can do that fairly well now. It needs to improve. I'm not very happy with its quality, but we're getting there. And I ended up deleting the picture for the diet level one, just for potential confidentiality reasons. But basically that's another difficult one where when we dispense diet into the pot, and we're doing that every few times a second for 24/7, there is drift. So as the diet consistency changes, it will slightly be too much, slightly too, and we can't have the diet proud, because then it squidges diet everywhere in our machinery, causes jams, and we can't have it too low. So we're trying to get that right so we can get the AI to train the diet or adjust the diet level. So very quickly on the future, I'm out of time. What we're doing now is doubling down on AI to get our efficiency up. My objective is to get 50 times more output from my 20 operating staff. So they're going to go from 700k rated capacity, we're not quite at that level yet. The factory we're building for 2026 will be 3.5 million, so 5x. 2027 10x, and a couple of years later 50x. And it's all done with 20 people as the aim. And it's multiple simple things, but ultimately we're going to flip across to be AI-led. I mentioned our operators are looking for where things have jammed and they're trying to correct it. What we want is the AI to know where it's jammed and tell the person where to go and what order to do things in, because it knows what's most important. And in a big factory, we won't be able to look at everything, but the computer can. So, yeah, we also want to do some more in the field, and I think our next speaker will tell you even more about the fun of spotting insects on traps. But we do monitor wild SWD so that we know where to release our flies. And the one I'm really keen to get onto is the one on the right. So the left picture with the red column bars is showing a map we generate every week for every field. This is where we found female SWD, and therefore we want to bias our releases to where those are found. On the right is a walking map. The two don't actually match, I'm afraid. I couldn't get the right photo, but normally the white diamonds, which is where we should be releasing flies, would basically correlate and have more white diamonds where there are more red columns. So releasing more males where we found more females. And again, that should be something we should be able to generate using AI. And last but not least, this SWD solution machine has been hard to build. But now that we've got it working, it should be very easy to adapt that to different fly species. Just change the diet, reprogram the software. We've already prototyped moths, and then we'll have another cascade. And mosquitoes is where I started, so keen to get onto those two. They need a water-based larval stage, so it'll be lots of fun. That's it, last slide. So BigSis, very much an AI-enabled business. You just could not do what we do without computers and AI. It's been a tough journey to get up to here, but now we're really at that inflection point, both for scaling the mechanics, but also being able to adopt more and more AI and computer applications to make us more efficient and ultimately profitable. I'll stop there. Thank you very much.
Thank you. So, yes, question. Cindy, sorry.
Thank you so much, Glen. It's such an interesting technology. I really love it. And I'm just wondering, what's the feedback from the farmer in terms of this sort of green way of pest control? What's the feedback? Also, what's the efficacy?
Yeah. So the feedback's very good because the efficacy is very good. I said right from the outset that SIT can outperform chemical insecticides, which is why I'm a believer in it. There's a lot of biocontrols like predators, parasites that have sort of 50% efficacy, to put it on a scale. Whereas we've got published data now, we've had 2 publications, and basically we can show that we got an 80% reduction in infestation of fruit, and that's really important to growers.
So if this was widely adopted in the UK,
Yeah.
how large a factory would you need to produce the insects to cover?
Yeah. So there's about 6,000 hectares of soft fruit. We're targeting blackberries, raspberries, strawberries, cherries, and blueberries because those are eaten fresh. By the time you get up to Scotland, they're starting to get invaded by SWD. They'll be our market in a couple of years' time. We're targeting a 50% market share, and that would need a factory that's 6 times the one we're going to build next year. So we're going to do that in 2 steps. This 3,000 hectare factory is probably at the lower end of what our eventual factory would be. So when we go to Europe or America, we'd build them for 5,000 hectares.
Thank you.
And maybe, it's roughly, it'll be less than 2,000 square meters per 1,000 hectares. So you're talking less than 10,000 square meters for a 5,000 hectare
But
factory.
that's just for one insect
One
species
insect.
for one crop.
Yeah.
So my daughter's doing a PhD on the diamondback moth, so I know that one as a major.
And a good target for us.
Yeah, okay.
It's on our list. Yeah, absolutely.
The models you're using, are they trained from scratch, or have you found these sort of pre-trained foundation models that are starting to be more and more available to be useful?
So the original 3 models, the egg and the adult and the male-female, I didn't do the programming, but my team was originally trying to build a sort of bespoke image classifier network. but ended up using a ResNet backbone and adaptation on that. And a couple of the others, though, that we're starting to do more sort of quick and easy things are done with smaller bespoke models.
Cool. I think we'll pause it there because I think we're at time. So thank you very much. And then, as you'll see, a sort of similar theme, but an interestingly different approach. This is Robert Fryers, who's the co-founder and CEO of Spotta, pioneering smart pest detection technology. All pests are getting in the ear tonight. Using AI and Internet of Things. As an engineer and Cambridge graduate, Robert aims to disrupt global pest control away from blanket chemical control to precisely use the exactly the right treatment in exactly the right place at exactly the right time. So, Robert.
So yes, my company, Spotta, is actually a very complementary technology to what Glen's been talking about. One of the things that really matters to me is the fact that I see an awful lot of AI out there, which is frankly frivolous nonsense. And I really, really want what we do to matter, to have impact, which is why I'm very pleased to share the stage with you guys this evening. Because I don't think it is a very good use of all that electricity. It's almost Bitcoin levels of wastage. And what we're doing at Spotta is something a little bit different. So, take an example here. I feel a little bit bad bringing hardware to an AI. It's slightly dirty bringing it to an AI event. But these are some of the examples of our products. We make monitors, IoT monitors for insect pests. So the key thing there is they are providing real-time data without someone having to go and look and inspect cards. So this is one of those sticky cards, very similar to the one that Glen was using, same as you can see in the side of this box here. Somewhere on here, there's a pest that has done about $10 billion of damage in the last few years in the Americas for citrus. They have used annually about 50,000 tons of pesticide, which is a polite euphemism for poison, on the land. And at the moment, nobody can really find it effectively. It's enormously labour intensive, and we use AI to find it and to report back on real time. Now, simplistically, if you're plugging this card into a cloud model and just piping all this data at extremely high resolution up to, doing it on AWS, it's a pretty easy problem. The really hard bit is when you're trying to do it in a cheap device that's got to be left in the field for years at a time without anyone having to touch it, and you don't have an internet connection. Then it gets a bit more challenging, and that's where our technology comes in. So here's another example, one of our technologies that we use. Exactly the same technology, in fact, different shaped box, basically. So we provide both a sort of strategic level view of a whole variety of farms, and then these monitors, where this happens to be a large beetle, in this case, weevil that kills date palms, going inside the device. First level of AI is identifying the species as it enters, and then we have another layer of AI when we've amalgamated data from many thousands of those monitors to allow people to actually then control and manage their field teams and send them to the right place and use, in this case, much more targeted intervention rather than spraying the entire thing from an aircraft like they used to do. They can now go and inject a very targeted case into individual trees. And in the future, hopefully, we'll be able to use something like sterile insect technique to avoid the use of chemicals entirely. So this is the core of what we do, 2 layers of AI, one inside the edge device here, and then one back at base once we've got that data back. Of course, we do have an internet connection, but it's very limited bandwidth, so we're not sending all of the images back up to the cloud, we're just sending the answer back up to the cloud because we're doing it over a satellite connection usually. So, and that allows us to do something about this, and this, and this. Pretty horrific. And one of the key challenges with basically all insect pests is that they grow exponentially. So if you can catch them even a little bit earlier, you make a massive, massive difference to the amount of damage they do, the costs involved in treating them, and therefore the amount of chemicals you need to use. And that means that we can do something about the horrific damage to biodiversity that insecticide use is causing at the moment, and has been for the last 40, 50 years. And in terms of impact, if we do this for even just a couple of insect pests, we're talking about equivalent to electrifying the entire road networks of large European countries. Just our little team in Cambridge, we've got 30 people, we're about a mile and a half that way, and we're already starting to have some of this impact, which I'm extremely proud of. So I was going to spend the last couple of minutes just talking about where we use AI and also our philosophy about it, because I think most of the people who are busy in this, I'm sure you're all familiar with the hype cycle, and we're clearly coming off the top of it now. Gone are the days where you can just throw AI on a pitch deck and someone will throw a few $1 million at you. That doesn't happen anymore. That was sort of peak 2022. But now, actually, people are starting to have to be a lot more considered, and this is something, fortunately, being a combination of hardware and software that we have a bit of an advantage in. But if any of you are thinking about building businesses in this space, having a think about where actually is defensibility going to come from, because the days of just being able to put a thin wrapper around a foundation model and pretend that that's a finished product that is going to be in any way defensible are gone. And for us, well, really there are these three key parts. You might be an expert in the market and know that sector and know exactly what you need to do. That's great. You might be building the model. You might have access to control over the data set, something unique. And we're quite fortunate in that we have some uniqueness in all three of those. Because building a lasting advantage as an AI company in 2025, we're already seeing this. Basically all of the foundational models, whether that's vision systems, whether that's image generation, whether that's language models, they're all basically asymptotic to the median of the internet, and it turns out that median content on the internet isn't actually that good. So you've got a few options if you're going to try and build a business about that. You can do it faster. You can raise $1 billion and buy half of NVIDIA's stock, and that's what OpenAI did, it's what Anthropic did. That ship's probably sailed. You can do very carefully curated data. This is how we got started, and actually being a lot more selective about what you feed into your model and what you build it around. But where it gets really exciting is where you control the source of the data. So we're putting these devices out into the field. We're the only people in the world with access to that data. Nobody else can build a model that can ever catch up with that capability. And it's only going to get better. We're not relying on generally accessible information that is at best going to get stale, and at worst is going to get flooded and poisoned by a whole load of AI-generated content, because we know where the data is coming from, we control it, we know its quality. And that, we're already pretty certain that we are the owners of the largest insect image database in the world. That might or might not be true, I'm pretty sure it is. But in any case, we're the only people who are deploying it in this particular space. So, yeah, just to summarise, basically, we have these devices, they go out in the field, we have a variety of different designs for different pests, a few different families. So this one, for example, does small flying insects, this one does small crawling insects, this one does slightly larger crawling insects, but fairly similar families of products, pretty standardised electronics and designed to be cheap and easy to deploy, and that's how we've managed to get to many thousands of these out in the real world, worldwide now. And one of the challenges that most of the other players in this space has had is just building good quality products. Actually, the combination of AI with something really defensible, like a bit of hardware that's really hard to reproduce and is a really challenging thing to build, actually leads to quite a strong business in a way that pure AI company or a pure hardware company doesn't really have. You can bring those two together, you've got something pretty unique, which is, and I can't claim that was the plan right at the beginning when we started Spotta, but it's worked out pretty well so far with that. So, yeah, a couple of other things that if anyone wants to ask questions about these, I have strong opinions on these, but I won't bore you with them unless you want to hear about them. So, yeah, that's me.
Very good. We should talk about that in the bar. Questions?
I wouldn't mind hearing how you got started doing this.
Sure.
What maybe you mentioned that the plan might have not been this at first,
okay.
and how you ended up with this.
So in 2016, I knew absolutely nothing about insects, but I knew a lot about low power sensing. So my co-founder and I, we spent the first 10 years of our careers doing things like pacemakers, other smart implants, where you're building ultra high reliability sensors and actuators to run for long periods of time without access to the outside world, basically. And our first business, we were consulting, and we were chatting to one of the big pest control companies, a name you'll all recognise, and we were sat in the CTO's office, and he put a rat trap on the table in front of us, and he said, I want a better one of these. Literally the better mousetrap conversation. I wanted to have a light on top to tell me if it's got something in it. I was sitting there with my co-founder Neil, and we looked across and said, so this guy, he wants us to build a smart device, but he still wants his worker to drive to the depot in the morning, get in the van, drive to the customer site, get out, walk across. He doesn't want to have to lift the lid. These guys don't get automation. There's an opportunity for us here, and that was what triggered the idea. We went away, we got digging. We soon came across insect pests as a much, much bigger problem. We started in the professional pest space, so this was our first product for detecting bedbugs in hotels, and actually of the 15,000, about 14,000 of them are this. Had the slight misfortune of launching this 6 weeks before the first COVID lockdown, which didn't do great wonders for our next investment round, but we got through that, we survived, and then from there we started bringing it out to outdoor pests and agriculture.
How do you, when the insect gets on there, how do you spot it?
Okay, so inside here, this design is is designed for typically 3 to 6 month deployment in the field, depending on which insect we're targeting. There's a carousel of about half a dozen of those cards in there, camera system mounted internally, so once a day we scan the card and have a look at it.
What happens when they get full? Does it tell you if they're too full, go and service it?
At the moment it's usually done on just a standard cycle, because even if one gets full, if one's not full, the one next to it might be, so we do it every 3 months. Longer term, yes, we might well get a bit smarter about that and tell them only when they need to, but it's not a huge burden, given that at the moment anyone who's using a sticky trap is going out and manually inspecting it typically once a week, sometimes once a day. You've already reduced the labour burden by 99%, doing the extra 0.9% doesn't have a huge impact beyond that.
Say you're gradually building up your data over time. It's certainly easy to get lots of images. How do you get the ground truth? Do you have somebody looking at all of them, classifying and...
Yes. Yeah. Short answer, yes. Yeah, actually, Mark asked me to mention that. It's that chicken and egg problem. How do you build up the data set? Yeah, absolutely. I don't think there's any super smart way of bypassing that step. Fortunately, with several of our products, we add a lot of value by automating the time spent going to the trap and coming back. Even if you spend the same amount of time looking at the thing to manually label it, you would have had to do that anyway, and you have saved at least the 2-hour drive up a mountain to go and get there to do that. So the economics are stacked up even from day one, even with human in the loop.
So you're collecting data about the flies. Do you collect any other environmental data, temperature, humidity, etc.?
Yes.
So that you know what conditions the flies, and can you use that data to...
Yes, absolutely. So as I was saying, we have the 2 layers of AI in our system. So one is inside the device, which is just identifying the species, and then separately back at the strategy map level.
Yeah.
Typically on most farms we'll have a weather station, we have temperature sensors in each device, we'll be bringing that information in, we'll be recording what treatments the farms are using. And using that, we're at the very early stages of this at the moment, but to build models about distributions and if the wind is blowing from this direction, and I know there's another farm over there that has a bunch of our monitors on as well, so I'm probably going to be looking out for the sort of stuff you'd expect.
So, those devices, I assume they are battery powered, right? So
correct. Yeah, some of them have solar backup as well, but yes, they're battery powered. Yes.
It's fine to run like 6 months.
Yeah.
Right.
Yeah, so I mean, a lot of our protected IP is about how on earth do you do AI on a device that costs a few tens of dollars, that can run for 5 years and only needs a battery, it's a single alkaline battery for 6 months at a time. And, that's a hard nut to crack, and that's the core of a lot of our IP.
What sort of farmer will benefit your technology the most? Is it a larger farmer, a specialist small farmer, or stop-through farmer, or crops, or what type of thing?
So we spend an awful lot of time thinking about which agricultural market to go into, and the main parameters we were picking on were someone who has a very clear, high priority insect problem, a big enough business that they will actually spend decent money, and frankly that doesn't really exist in Europe. From what we've seen, and where our data lets them do something very different. So when we've looked at that steered us very strongly towards horticultural crops, so fruit, high value fruit crops, because the crop is more valuable. They're typically growing one thing, so they have the same problems year after year, and it's a much simpler value proposition than say an arable farmer who's doing a crop rotation of half a dozen different things. They're dealing with different pests on different fields. To be a value-adding system for them, you've got to not cope with one pest, you've got to cope with probably 10. We absolutely could do that, but it's a much harder job to getting to the point of being able to do that. And then even when you do, your value per hectare is a 20th of what it is in a fruit, for example. So we have focused very strongly on fruit crops in countries where there are big farms. That's where we've had most traction so far.
Do you also track the good insects, pollinators, and so forth?
Yes, not as much as I'd like. It's something I want to spend a lot more time. We try not to get, particularly for the ones that catch the insects. We don't want bees on that.
Yeah.
That's not good. But for some of the other ones that are flow through traps, so for example, this is one that we use in forestry, where we're tracking the pest species, we're tracking a couple of the key predators of the pest species, and with them a general biodiversity index, and we report all of that back. So for example, we were working with the Forestry Commission with that product, and we were able to show that when they switched from blanket sprays to targeted manual sprays onto each tree, the impact on the pest was just as effective, but they halved their impact on every other insect, and that was quite a nice thing to be able to help demonstrate and deliver.
And then Colin.
I think coming back to this tight margin problem for farmers, I'm curious about the pricing structure. Do you charge per hectare, per
hectare per year? Yeah.
Okay.
Yeah, and it's value-based pricing at this stage. We don't have any really credible competitors. So, but there's also one of the other selection criteria when we look at a new market is people are already monitoring, because there's a very clear basemark of, I've already got 10 people on my farm who are just going around looking at these traps. Okay, now there's a clear ROI there. Trying to persuade someone, like you were saying earlier, in someone to do something completely new in agriculture, you need a huge amount of evidence that you're going to add some downstream yield benefit. Whereas if they're already spending money on it, you just have to prove that you're more effective at the same price or cheaper than what they're currently doing. So it's a much quicker sales cycle.
Do you use AI in the manufacturing of the actual traps themselves? So I think you mentioned that it was used in detection.
Not in the way, for example, Glen was talking about, no. I mean, we're building these in batches of a few thousand at a time. It's a fairly conventional manufacturing process. It's the usual QC processes that good quality manufacturers used for decades. There isn't really much call for AI. There's a couple of very specific cases that we do. So every device will have an image quality test where we're using AI to basically check, is it in focus, is it catching the right area, is the lighting correct, all the rest of it. So that is we've got a model we've trained specifically for that step, but not as a general, has it been put together correctly, no.
Very good. I think we should say thanks very much to Robert there.
My
and
pleasure.
continue to Thank you very much. Thank you very much to all of our speakers, to Ian, to Glen and to Robert. Fascinating presentations. We are back on the 13th of November for a special event in Mishkondaraya, just opposite the station, about AI and legal tech, and looking forward to that. But in the meantime, please go and enjoy a drink and a pizza, and probably more questions for our panelists. So thanks very much for everybody for coming.